Welcome to my TikTok presentation of Applied Physics. My name is BV Raghuraam from CSE AML C section. Today my topic is about the differential efficiency of quantum well lasers, in short known as QWL. The quantum well laser QWL has by now a few well established properties at variance with those of now well understood double heterostructure DH laser. It has extremely low threshold currents, well below those predicted by the simple extensions of DH laser theory. Temperature coefficients of the lasing threshold current to sometimes better, but also sometimes worse than DH lasers. High frequency modulation capabilities, low degradation rates, etc. It is therefore interesting to understand the physical basis leading to these operational characteristics, as they are intimately related to the two-dimensional nature of electron states in structure. The purpose of this short review is to demonstrate the operation of QWL is strongly connected to the bidimensional character, and that it actually is good laboratory to understand the pros and cons of low dimensional devices. The extension of QWL concept towards lower dimensionality will briefly address at end of this presentation. The two main opposite effects in QWLs, the number of available quantum states in active region is strongly diminished in the z-0 direction, that is perpendicular to the active layer plane. The thickness of the order of 200 or less reduces the allowed value of momentum in the direction to one or a few quantized values within occupied states at threshold, that is few kt above the ground state, whereas the number of occupied states in 1000 DH laser would amount to a few tenths. The efficiency of emitted photons to interact with an electron-hole pair to induce another stimulated recombination process is strongly reduced because of the poor optical confinement and has two origins. Firstly, its small confining material thickness. The wave guiding properties of DH are poor, and the usually confined optic wave tends to natural extension of one wavelength. The more or so the confined layer thickness diminishes. Secondly, the rather wide optical wave has an overlap with the active layer, which diminishes as d. Therefore, both effects tends to diminish the optical confinement factor R as d2 with good approximation expression as 4. The expression is as follows. T is approximate to d by lambda naught whole square into 2 pi whole square n delta n, where lambda naught is the wavelength in vacuum n and lambda n are the averages and differences in indices of refraction of the materials of the DH. From preceding discussion, it is clear that in single quantum lasers, the diminution in R is unacceptable unless a SCH scheme is used. The other alternative, that is the use of immutable QWS, will be discussed later. Overall, one calculates the decrease in the number of states tend to just balance the decrease of quantum states to be inverted at threshold. And here we can see single quantum well, multiple quantum well, SCH quantum well pictures on the right bottom side. The more subtle effect in 2D QW lasers. In order to analyze in more details the operation of QWLs, one has to consider the following effects. The square 2D DOS led to several specific effects. Gain remains finite even for low hand fouling in opposition with DH lasers, where the DOS and therefore the gain tends to 0. This implies that the gain versus current curve is steeper than in 3D, and also that temperature operation of QWLs will be excellent with threshold currents reaching to very small values at extremely low temperatures. And here we have the graphical representation of density of state, electron distance, and special gain. The GAAS or GAIAS case. The numerous laboratories have reported excellent results on GAAS single quantum lasers. Besides their low threshold current, which is understood in terms of above mentioned improvement factors, several hitherto unexplained results only recently received complete explanation. The advantage of GRIN SEH structure over SEH is due to their smaller device in light confined layers. In normal conditions, the detailed calculation of carrier densities at threshold yields at quasi-Fermi level, which is quite high in quantized layers, typically 60 m electron volts. On the other hand, optimal 2 is not averages associated. It has low threshold QWS. Standard MQW lasers have better 2 than DH. GRIN, SEH and SEH lasers in decreasing order of merit. MQWS, the most two-dimensional lasers as the potential barriers of confined materials, is the highest and therefore limits carrier leakage. In that case, the Fermi, di, di, Fermi Dirac tail, unuseful electrons because of uninverted, is smaller than in 3D. SQW versus MQW laser operation. As seen from figure 3, gain appears at low injected current. The model gain Tg variation as a function of injected current density for various numbers of quantum wells. Note the saturation of the Z is equals to 1 quantum state for the single QW laser above X 100 A per centimeter square and the onset of N is equals to 2. Quantum state transition leads to higher gain at 300 A per centimeter. Net gain starts at higher currents for increasing number of wells because of the increasing number of states to be inverted. Well thickness is 100 A. And on the right side, we can observe the current density and modal gain graph. The gal N AS INP and gal N AS TN AIAS QW lasers in strong contrast with GAAS slash or GAAIS material system. No laser emission could be obtained in SQW lasers in GALNAS material cases. The situation arising is clearly shown in the figure on the right side and is measured gain curves. As carrier injection increases, heating of carrier occurs, presumably by Auger effect. It decreases the carrier inversion, that is, the gain, increases dramatically the confining layer population, the structure on the right side. The graph on the right side is showing us the photon wavelength A between photon energy and photoluminescence intensity. Additional properties of QW lasers. Beside their good current threshold and TO, QW lasers possess a number of additional important features which makes them highly useful. First, modulation limits. Due to the high differential gain dg or dz of QWLs where less, the injected current Arkawa and Yariv have shown that an increase in speed response of a factor 2 times could be expected from QW lasers over DH lasers. This was confirmed by Yomi et al. Spectral line width. From the same high differential gain in QW lasers, Arakawa and Yariv have predicted narrower line widths than in 3D DH lasers. Although this improvement has not yet been directly measured. The related line with enhancement factor 51 is diminished by 50% in QW lasers as compared to DH lasers. Third, reliability issues. Although relatively few degradation studies have been reported, measured net optic gain curves top and corresponding calculated curve from modal gain Tg. The low energy side of gain curve is not treated in the theory as no band tailing is included. The high energy slope of the gain curve is well represented by calculations. Impurity-induced interdiffuse or IID for short. Impurity-induced interdiffuse of quantum wells have been evidenced in many material systems with various PN-type implanted species. It allows to transform an implanted region with thin wells and barriers into an alloy with average composition. Such an alloy has the usual properties of light and carrier confinement. Therefore, one can use such an effect to construct a variety of strip geometry lasers, window lasers, that those are lasers where the active regions do not extend to the external facts, etc. Excellent results have been obtained by such techniques, which permit to manufacture complex devices with simple planar type operations, while one would otherwise require multiple step etch and decomposition processes. Evolution towards 1 and OD. The importance of situations. It is by now quite well established that interface disorder is limiting recombination line shapeness in quantum wells. Although some recent interrupted growth experiments evidence excellent improvement, however, at the expense of high impurity incorporation. The required high density of states, that is, high number of ion OD systems, as is evident from the above discussion of 2D QW laser, one cannot diminish too much the active material volume for two reasons. First, required carrier density per 1 and OD well are so high that total band filling would occur before enough gain would be obtained. Second, the confinement factor would be vanishingly small. Thank you. Here, my TikTok presentation about the efficiency of quantum well lasers and hope you have understood more about the lasers, QW lasers, SQW lasers and other things. Thank you.